That was really good practice for the opening, though. It was. I thought, like, you did it so convincingly, I thought I was like, "Oh, I'm not looking at the camera for the start of the show." I was really nervous. Never. I don't get nervous anymore. No. Me?
Hello, universe. All right, I'm gonna toot my own horn here. I actually recruited Kimberly for Weekly Space Hangout.
It's true.
I don't. When would that have been?
That was
2015, 20.
that was early 2018, I think, or late
It
2017.
couldn't have been that late, could it have?
No. Maybe no, I think it was late 2017.
Yeah,
Yes.
so both of us were working for a now defunct website called Space Exploration News. And at the time, we were the only two then graduate students working on the project. And I was like, hey, I know something you might like to do.
Yeah.
And
Morgan was like, hey, look, another grad student. Hi. And I was like, hey, another grad student. Hi. And then he dragged me into this thing. And it was awesome.
And however many years later, Kimberly was sitting on my balcony last weekend.
That's true.
Enjoying an afternoon.
Yeah.
That is.
I was visiting Nashville, and I was like, hey, look, my friend Morgan's in Nashville now. It was awesome.
That is absolutely amazing. My audio levels are quite high. I need to fix that. So that opening that you said was so professional, it did not actually go out to the audience. So apparently I can be very practiced in what I say, but not in what I produce, or very practiced in what I produce, but not in what I say.
Ian, can you tip your camera down at all?
Yes.
Or sit upper? Yeah.
The
Awesome.
down is much better. All right. So we're just pulling things together, making sure everything is all set up before we do the official opening to the show. All right. I now have healthier audio levels. Okay. Yes, Series U here, Dr. Pamela. I am now sharing my audio with the world. All right. So we have many things to talk about this evening. I am going to ask Ian one more time. The goal is to touch the top of your head just barely to the top of your field of view, just barely. Your monitor doesn't want to tilt.
It won't remain entirely stable if I do.
Oh dear. Okay, stability is greater. We can make this work. All right.
Is that better at least?
Yes, that is much better.
Yes,
Thank
much better.
you.
Obviously, video production is not my forte.
It's all right. You're not here to talk about video production, so we're good. All right. Let me get my notes up in front of me, and we will be ready to go. Wait, Ian, I should have asked this before we were semi-live. How do you pronounce your last name?
Think of a cup of coffee. Jakupca.
Jakupca.
That's it.
All right. So I'm going to press the record button that none of you ever are aware of me pressing in the background. Fancy. And here we go. Hello, everyone, and welcome to the Weekly Space Hangout for today, June 1st. I am not Fraser Kane. I am Dr. Pamela Gay, and I am filling in this week while Fraser is off doing wonderful things with his family. And he's missing out because I have an amazing group of humans joining me this evening, and we are realizing we have one of the more senior roundups of reporters here on the weekly Space Hangout. Joining me are Dr. Kimberly Cartier. How are you doing, Kimberly?
Hey, Pamela. Happy podcast day. I'm
Happy.
doing great.
That is excellent. Happy podcasting day to you. And Morgan, Dr. Morgan Renberg is here as well. How are you doing, Morgan?
Hey, Pamela. People don't know that you're always lurking behind the scenes on the show. It's so good to have you join us this week.
It's true. I've been producing the show in the background, pressing the buttons, making things
And doing
go.
a great job of it.
I try. I don't always succeed, but I try. But you guys are awesome, and I'm going to get to spend the entire second half of the show with you. But before we can talk about all the news and glory that you bring to this episode, I feel I need to introduce our special guest, Ian Jakupca, whose name I'm sure I just mispronounced because he said it's Jakupca, and I did not actually say that. Welcome, Ian. I'm so glad to have you here and to do as Fraser always does. Who are you and what do you do?
Well, thank you, Pamela, for inviting me here. What do? I work at NASA Glenn Research Center. I am the fuel cell technology lead here. So it is my job to coordinate research and development activities for fuel cell power generation and electrolysis of water to do all sorts of good things with hydrogen and oxygen gases.
That sounds like a perfectly reasonable and highly technical thing to do. So we're going to take this back and try and break down a bunch of these words. We've started hearing a lot about fuel cells, especially in relation to electric vehicles, but I'm not sure many people really know what a fuel cell is. Can you break it down for us?
Well, absolutely. A fuel cell is an electrochemical device, which means you take chemistry and you do something magical with it and you end up with electricity. That little subtle magic can be interesting. It depends on what you're doing. What we're talking about here for NASA space application are basically using hydrogen and oxygen as a chemical storage mechanism. So you take water and you put energy into it in the form of electricity and you break it up into hydrogen and oxygen. And that hydrogen and oxygen stores chemical energy so that when you need it, you put the hydrogen and oxygen into a device called a fuel cell. And that fuel cell combines the hydrogen and oxygen to release the energy you put into it in the first place. Here on Earth, we can pull the oxygen out of the air. There's roughly 20% oxygen in our atmosphere. Pure oxygen can be kind of a hazardous device or hazardous chemical. So you don't want to use ultra high purity oxygen unless you absolutely have to. So use the atmosphere. It's easy, it's safe, it's available, works wonders. Unfortunately, NASA goes places where atmospheres really don't exist or are not particularly useful. So we bring pure oxygen with us in order to do that, in order to support that chemical reaction. Some of the places where we look to put fuel cells, Earth, obviously. NASA supports a lot of electrification of aircraft activities. So we're actively working on projects to support air transportation of people and cargo for a hydrogen economy.
That's cool.
Some of those require batteries, some of those require fuel cells, very, very application specific. But since NASA is interested in more than just Earth, we're looking at other places too. You've got what we call cis-Earth, and that is all of the space near Earth, low Earth orbit, middle Earth orbit, high Earth orbit, and the transportation spaces between our Lagrange points and the moon. After that, we're considering fuel cell power for Mars applications, particularly for sustained operations. If you need seasonal energy storage, batteries don't work very well. We'll get into some of those details later. but for seasonal storage, fuel cells make a lot more sense than batteries.
So basically, fuel cells are devices that allow us to take advantage of the fact that water is a lower energy state than free hydrogen and free oxygen. And your fuel cell here on Earth is carrying your hydrogen and using oxygen from the atmosphere. But it gets a little tricksterier when we get to other places in the solar system.
That was 90% correct. The subtlety in there is that the fuel cell is like the engine in your car.
Okay.
It, in and of itself, is just a conversion device. The hydrogen is a fuel. You have to provide the fuel to the fuel cell stack for it to work.
Okay.
It is not intimately stored with the fuel cell stack, which is what gives it its very, very, very high specific energy and specific power compared to batteries. A battery combines the chemical storage with the energy conversion devices. That way you have a very fixed specific energy, specific power, amount of power available per unit mass. A fuel cell separates the energy conversion from the chemical storage. So if it's like your car, if you want to go faster, you get a bigger stack. You don't build a bigger gas tank, but that's what you got to do with a battery. So if you're comparing the two, a fuel cell and a battery can kind of do the same thing, but a fuel cell is much more tunable than a battery. You can fit your application needs much more tightly if you're using a fuel cell, if it makes sense to use that technology.
So why aren't we using fuel cells like everywhere then? Like, why isn't my phone a fuel cell? Why isn't my car a fuel cell?
Well, while hydrogen is the most abundant element in the universe, it is sometimes hard to get a hold of. And you don't want to carry around a dirigible to make sure that your cell phone is running for a week and a half. I mean, that's just silliness. What's shown on the screen here, a Argoni plot is on the left, and a grossly simplified version of it is on the right. And it depends on how much mass you want to take with you and devote to your energy storage system. If you have a lot of energy, but your charge and discharge time, the amount of time that it takes between opportunities to plug into the wall, if that time is short, use a battery. It makes life simple. There's no moving parts. It's all solid state. It makes life easy. But if you're on board a spaceship like the Space Shuttle or the Gemini pod or the Apollo service vehicle, your vehicle dynamics are such you can't have solar arrays, and your energy storage is so big that your battery mass won't work because the batteries tie the energy storage and the energy conversion into one unit. By separating the two, go ahead.
Now, I was going to say, let's take a second to step back and think about that, because this is particularly an issue with going to the moon. On Mars, we have to deal with the day-night cycle, but nights, I mean, they're essentially the same duration they are here on Earth. The Mars day is only about 45 minutes longer. And we know how to build batteries to keep things going overnight, because we have to do that here on Earth. But on the moon, you're dealing with a half-month-long night. And as we look to build things to go to the moon, we generally are like, it'll last one lunar day. And that's good. And this is that battery problem. Whereas nuclear fuel RTGs, radiothermal isotope generators, they just keep generating heat. They're good, they're good, they're good. Other forms of power generation, if we wanted to, we could build engines that worked on other fuels that chewed through the night. And fuel cells, it turns out, is about the most effective way to keep things going through that 2-week-long night.
Thank you. That was a spectacular segue. Yes, the existing nuclear technologies work well for very small power level systems, generally 100 watts or less. But for lunar surface missions, particularly a habitat, you're talking tens of kilowatts. And to maintain that much power over a 2-week Earth period, that's a lot of MMRTGs. That's an awful lot, and you're not going to be able to fly those. A
Yes.
fuel cell is not tied to the Carnot limit. It is not a heat engine.
Wait, the what limit?
Carnot, C-A-R-N-O-T. For those of you who maybe remember your distance thermodynamics, and I don't know how many years ago, it is a difference between your start temperature and your stop temperature, and that limits your efficiency. You can take hydrogen and oxygen and burn it inside an internal combustion engine. Best case scenario, you're talking 28% efficient, 30% efficient at best. And that's just the mechanical conversion. Now you got to get that mechanical energy to electrical energy. Whereas a fuel cell will take that same hydrogen and oxygen and generate electricity directly at approximately 60 to 65% efficient. So that for each pound of hydrogen and oxygen you take, you've got roughly 2.5 to 3 times the electrical energy available. So that's a pretty big savings. Plus, depending on the electrolyte chemistry, you can end up with high quality heat. Helps to keep systems alive during the very cold lunar night. I mean, 100 degrees Kelvin is cold enough to turn oxygen into a liquid just resting on the moon.
Yeah.
Okay. When we talk about mining water ice on the lunar surface during the lunar night or in a permanently shadowed region, that water is almost as hard as granite because it's so cold at those temperatures. So it's a very, very challenging environment during the lunar night. Fuel cells generate both heat and electricity. So you're addressing two of the major concerns to survive through the lunar night.
Now, you used the word electrolyte, and I have to admit, as an astrophysicist, I see the universe as hydrogen, which you're talking about. I'm good. I understand hydrogen. Helium, you haven't mentioned that. And everything else is a metal. That's the way us astrophysicists think. Now, you used electrolyte in a way that wasn't referring to energy drinks. In the context of what you're doing, what does electrolyte mean?
An electrolyte is any material that carries a charge. So when you have an atom and it loses or gains an electron, it is charged. So you have either an anion or a cation. And an electrolyte allows preferentially one of those ions to cross from one side to the other. Depending on how your battery cell is set up, you can generate electricity with that. And depending on how long you want this to go, we can get to electrolyte chemistries. There's a lot of them out there, and they each exist for a reason, and they serve a very specific function. What we're looking at for space are low temperature proton exchange membranes, which are like the saran wrap in your kitchen, and they conduct protons, hence the proton electrolyte. We're not very imaginative, we engineers. What that does is it allows hydrogen to go from one side of your membrane to the other, and it generates water in the oxygen stream. So you're humidifying your oxygen stream. That's at low temperature up to 80, 85 degrees C. The other technology we're looking at is called the solid oxide ceramic. Think of your dinner plate that's in your kitchen. It's very inert at atmospheric temperatures, right? Now you can drop it on the floor. Your pets can help clean up whatever leftovers are still on the plate when it hits the floor. But when you take it up to high temperature, it moves oxygen from one side to the other. So the water would get formed in the hydrogen cavity, which is good for ISRU applications, in situ resource utilization, making what you need from what you find where you were. Exactly. So, and we'll get to this slide in a minute, but those different chemistries provide different fringe benefits. And for anybody who's ever built something, Nothing is perfect. It's a series of trades to find out what works best for your application. Electrochemical systems, they have some version of them everywhere. Within NASA, we use them for life support, the ECLS, ECLSS, right now on board the International Space Station. There is a PEM-based electrolyzer that takes leftover wastewater that's been cleaned up and generates breathing oxygen for the astronauts. It's been running 18 years now, so it's generating a lot of oxygen. It works well. It does what we need it to do. One example of electrochemistry. For power, we just talked about power not too long ago. Propulsion is probably the oldest use of hydrogen in NASA. You burn it, you generate thrust. It works spectacularly well in the vacuum of space. And then ISRU, in situ resource utilization. Here on Earth, we've had 10,000 years to make a commercial marketplace that can deliver what we need more or less when we need it. But we don't have access to that when we're on the moon or on Mars. We need to start building stuff with what we find when we get there. Otherwise, it's going to be very, very prohibitively expensive and take a long time to get what we need to support a sustained presence on either the moon or Mars.
Now, one of the benefits of fuel cells is we are looking to be able to do in situ resource utilization using either the water we find or the hydrogen we find. But it takes energy to access the resources someplace. How does the balance work? How do you get the system going as we look to move beyond our planet?
That is an outstanding question. For the lunar surface, it's solar power. For the near-term applications, it's going to be solar power because sunlight is ubiquitous and more or less, and again, very site-specific, it's always available during the lunar day. So you've got lots of free energy. The trick is, how do you store it? There was a term I used earlier called specific energy.
Yeah.
Batteries have approximately 160 watt hours per kilogram. A regenerative fuel cell can be upward of 800 watt hours per kilogram. So that's a lot of science payload that you can take if you're using a regenerative fuel cell compared to a battery. So that's why we're looking at that for energy storage. But the source of the power for near-term moon applications are the sun. When you're getting to Mars, where the availability of sunlight is significantly reduced, that is a much more open question. It is possible, based on recent experiments, to support a lunar base from PV arrays. Chances are good, though.
Photovoltaic.
Sorry. Yep. NASA, we really like our acronyms.
It's all right.
Yeah. On the Mars surface, yes, it will eventually become some sort of nuclear power plant to support a sustained human presence on Mars. It's just a question of when can we get that infrastructure in place.
It sounds like all of this is a puzzle of figuring out. All right, so we start off by building all of the solar panels and the initial sets of batteries on Earth. We go to cislunar space and we do the stuff and the things, and we get to the moon and we use the daylight hours with the solar panels to harvest the resources. We then use the resources that we've harvested to help us get through the night, still using technology brought from Earth. How do we take this cycle and get to the point where instead of living off the Earth in space, we are living in space?
Closing all the biological loops and the material resources?
I'm only talking energy here. Only energy. We're going to stick to energy tonight. I like you.
I appreciate the delicacy of that. right now that energy loop is more or less closed when you use solar power,
Okay.
because that is an overabundance. You just have to size your system appropriately. The International Space Station has been flying for years, and it's not getting any power from Earth. That would be one long extension cord. It would be a really heavy extension cord, and we didn't make one.
That
So on the moon, the trick is finding an energy storage source that is light enough that we can expend the resources to put it on the lunar surface.
Now, I have enough friends with solar panels that I have looked at their batteries and decided that that was more weight than I felt the first floor of our house could support. Can you help our audience get a sense of, just when you say batteries weigh a lot, what does that mean?
Well, that was that number 160 watt hours per kilogram. That is
Right.
an energy. It's a conversion to joules. For those of you who like the scientific units,
So
it is.
let's say to keep 3 people alive, roughly how many kilograms of batteries are we talking?
Well, here's the trick. You're talking power and energy, and the
Yeah.
difference here is time. How long are you trying to keep them alive? If you're
One
trying to
night,
keep them,
just one night.
okay, you're really demanding here. Um, that depends. You're presuming roughly 2 to 3 kilowatts of electric power for minimum life support systems over 12 hours. Okay, so figure 3 times 12, that's 36 kilowatt hours of energy. Okay, um, for the sake of easy numbers, um, let's say that you've got a crew of 4 people. So that's roughly 16 kilowatts worth of energy, and you want to keep them alive for 10 hours, slightly overnight and whatnot. That's 160 watt hours. Okay, so that would be approximately 1 kilogram or 1,000 grams, kilogram of battery weight. So you would look at, for a regenerative fuel cell, lots of caveats tossed in on this one, you would be looking at roughly a third of a kilogram of energy storage comparatively.
Okay.
And that's comparing a regenerative fuel cell to the same lithium ion battery chemistry that's in probably everybody's cell phone.
So a third of a kilogram to a kilogram feels like nothing to stress out over, but you're just talking one Earth night here. And as we start thinking lunar nights, that's going to go up. And so all of it compounds. And then we don't normally think about just how much fuel is needed to launch things. So it just gets more and more complicated as we go. Now, with fuel cells, there's a lot of concerns about things like, do we have enough lithium to keep the lithium economy going readily? What kinds of solutions are we starting to think about for some of these problems as we look beyond the surface of our world?
Well, the aerospace market right now is a niche market. It's very
Yeah.
small, and I don't want to say cost is not a concern, but weight is the primary concern. Fuel cells, aside from the platinum metal groups, everything else is pretty simple to come by. That lithium economy, the cobalt economy, all of these other precious metal and rare earth metals that go into lithium ion battery systems don't apply to fuel cell systems. So you only have to worry about platinum, which I admit is a very expensive material. So for getting that to the lunar surface, we're not to the point yet where we're worried about sustainability on the lunar surface. If we're starting to worry about sustainability, that means we are already sustaining. And we're not yet, we're still trying to get the first footsteps back on the moon after almost 70 years now. So
It
it's
it's not that bad. It's not that bad. I'm not that old, and I was born the year after Apollo. Um, yeah. I was born the year after. I'm not 50 yet, so it's not even 50 years since the last landing on the moon. All right, I'm going to stop being defensive now. So as you're looking to build this new sustainable way of living, we're looking at the Earth, Moon, Mars, asteroid belt, but that first place that we're going is with the Artemis mission to return to the moon. And how is all of this fitting together right now for you?
For the fuel cell technologies and electrolysis technologies, it's
Yeah.
going together reasonably well. I am the principal investigator for a regenerative fuel cell system that is intended to be tested inside a thermal vacuum chamber at Johnson Space Center. This vacuum chamber will simulate a lunar day-night cycle on the moon. So it will generate the roughly 100 degree Kelvin night and the roughly 105 degrees Celsius lunar day. And that is quite a challenging thermal environment. But that is just one part of the many different systems that need to go together. The moon is a spectacular laboratory. It is a great crucible for technologies. And we need that crucible in order to prove the technologies so that they can have the durability and life they need on the Mars surface. If something goes wrong on the moon, we can get back to Earth relatively quickly. If something goes wrong on Mars, it's not a good situation. So we want having this really challenging environment of the moon close by actually makes our exploration process a little more streamlined.
Mm-hmm.
So we have an opportunity to address many of the technical challenges associated with closing all of the biological loops, starting to close all the material loops, addressing wastes, particularly packaging. How do we handle all the packaging that we generate? How do we recover oxygen? Because if we were to bring along all of the oxygen we would need to survive the trip just to Mars, that oxygen tank would be larger than the entire volume of the currently envisioned International Space Station.
That's a problem.
That's a problem, which is why we're looking at a number of technologies to recover oxygen from carbon dioxide. And that is just one of the many techniques we're looking at to close all of these biological cycles to survive to and thrive on our surface.
All right, that is all amazing, and I don't know where to go from here, so I'm going to say, what parting thoughts do you have for our audience before I let you go and we start talking about other news in this solar system and beyond?
Just keep questioning. There's lots of technologies out there. Keep dreaming up ideas. Ask questions, ask questions, ask questions. Because without the questions, nothing gets advanced.
And if folks want to learn more about you and everything you do, where should they go to look?
Yeah, right now we're go to the NASA.gov website. You can also go to the Lunar Surface Innovation Consortium website. NASA has partnered with the Johns Hopkins Applied Physics Laboratory to coordinate lunar exploration activities, and you can find some of our work up there.
Thank you so much, Ian. This has really been a pleasure, and I know I learned a lot about fuel cells I didn't know, so thank you very much.
And thank you for taking me. Enjoy.
Okay, bye-bye. All right, so it's just us, folks.
Oh, that was very cool, getting all that detail.
Oh my goodness, I learned so much that I did not know about fuel cells, and just like the whole balance of which energy source you use at which stage of emission was just super cool.
Yeah, and it's a lot more complicated than the whole, it makes the water you need, that is usually where things begin and end in the discussion.
Surprise,
So-
spaceflight is complicated.
Yeah. Who knew it was hard? I guess I'm just gonna have to go back to my backup plan of being a surgeon.
Yeah.
Okay, I shouldn't try and do humor. All right, so if I seem a little bit punchy and tired, it's because I went out to see the Tau Hercules, and so pretty much pulled an all-nighter Monday into Tuesday. Did either of you get a chance to give it a listen on your radio, give it a watch in your skies?
Oh, I didn't even know.
I've just
How?
been enjoying the pictures from other people.
Yeah,
Well,
I'm
it
out
was
of the loop on everything.
it was supposed to
I
be a
live
storm. It was not a
you,
storm,
Pamela.
so
I
it was
live
fine.
vicariously through you.
Yeah, it's we estimated at about the best that it got. There's about 3 meteors per 5 minutes, and most of the night there was 1 to a few per 10 minutes. So it was definitely a meteor shower, but the 1,000 per hour storm that was predicted did not come through. But it was a good excuse to go camping. Somewhere in southern Illinois is a raccoon that stole an entire bratwurst from a pan that had a lid on it. Kudos to the raccoon. You deserved your plunder.
Life finds a way.
But there was, while I was off camping, there was science going on, decisions being made, and companies getting to celebrate some of the potential successes of what they had done. And I think that that's where we're going to start, is with Morgan and the story of, well, what are you going to talk about, Morgan?
Yeah, let's talk about the Boeing Starliner test flight. And it went up, it did space things, and it came back down. And that's a little bit better than they did last time. So I think NASA's calling this test a success. Like any initial test, it had its flaws, things to work on, but it was a clear improvement over their previous test that launched in late 2019, if you can remember back that far. On that mission, they got up there, but they had so many issues with sticking valves that they sort of burned through all their fuel trying to resolve that, and didn't even have enough fuel to reach and dock the space station to sort of do all of the various mission stages to simulate what a crewed mission would look like. So they brought that spacecraft back, and then Boeing basically paid $500 or $600 million to refly that test mission after several years of further development.
And that's a super important point. Boeing paid for test flight 2. NASA paid for flight 1. This was something Boeing kind of had to do to prove the worth of the mission program.
Right. They had been going forward in the past, sort of relying pretty heavily on simulations to complete various mission test stages. And after the first set of errors on the last mission, they've really kind of gone back and done a lot more physical testing of the spacecraft. And if the issue they had on the first one was primarily with valves, this mission, their issues were largely around thrusters. Now, misfiring or not firing thrusters can also be stuck valves. So it'll take a little bit of time, I think, to dig into the engineering data to understand what happened. But they had issues with basically all 3 sets of thrusters on the spacecraft. So of the 20 main thrusters that were used to lift the capsule from its initial orbit to the space station, of those 20, they had 2 failures. Then as they were approaching the space station, of their reaction control thrusters that were used to sort of orient the spacecraft in space, they had 2 failures there, although eventually those thrusters started working again. And then during the re-entry phase, as they were braking the spacecraft from orbital speed to the point at which the heat shield could take over, they had a failure on one of those re-entry thrusters as well. Now, none of those sets of failures were such that they would have caused a serious issue for the mission, but to have 5 issues is quite a few. And in part, Starliner relies on a very large number of thrusters, more so than Crew Dragon does.
Yeah.
And when you do that, you do gain redundancy, and so more thrusters can have issues before you have a problem. But it does mean that you have a lot more complicated machinery feeding fuel to all of those thrusters, and so your sort of surface area for problems is also larger. And so that's something I'm sure that they'll be taking a close look at in the engineering data. But the results of the test were significant enough that NASA has already sort of pointed the way for the next test, which will be the crew test. And so they'll load the capsule up with astronauts, send them on a couple of week mission to the space station, and then bring them back. And then once that's done, in reality, basically, that's the start of normal operations, because you wouldn't put people on it unless you believed it was going to work. But once that test happens, then NASA will formally accept the spacecraft for service, and then the contract that they signed with Boeing many years ago will sort of begin. So it's administrative beyond this point as much as anything else. And we can expect to see that test flight as early as the end of this year, but I think more realistically, we're talking about the first half of next year. And at that point, assuming all goes well, and with people on board, of course, we doubly assume that, then NASA will have 2 successful, useful American-made ways to get astronauts into space, really for the first time ever. There's really been no time in the past in which one country has simultaneously flown multiple human-rated spacecraft systems, and so this will be an amazing capability for NASA to have the flexibility if an issue were to crop up in the future in one of these, to keep that reliable access to the space station.
Now, while it flew without any humans on it, it didn't exactly fly empty.
Yeah, so they had this cool crash dummy in there to simulate the effects that the crew would be feeling in terms of vibrations and things like that during the course of the mission. And of course, you test all that stuff on shake tables and things during development of the spacecraft, but vibrations are weird things, and you never know that you're not going to find some sort of strange resonance between, say, the spacecraft and the rocket that you really could never 100% simulate. And so collecting that in situ data can be really valuable to make sure that you're not going to, deliver astronaut milkshake to the space station.
Oh my goodness, please never say astronaut milkshake like that again, ever.
Thank you, Kim.
That is the most horrifying thing I think I've heard in a long time.
Yeah, especially considering, unlike SpaceX, they're landing on land.
Right, yeah, absolutely. You want that ride to be smooth.
And
I think if I could sort of offer one sort of big picture takeaway from this, it's that this fixed price contract setup that NASA approached for these commercial spacecraft have basically worked. In no other era of NASA development would the company have footed the bill to repeat a test that NASA had deemed failed. And so, this was kind of a brave and somewhat questionable decision in 2011 when these contracts were being signed. But the end result is 2 spacecraft that appear to be ready for service for humans at a cost that really didn't change from what they thought it would be in 2011. And I wager you to find one other NASA program in the human spaceflight period that experienced 0 cost overruns over the course of the entire development cycle.
well, the cost overruns were just footed by somebody else, but I'm in favor of that. So there is actually a third mission out there waiting in the wings to get its moment to dock, and that's the Dream Chaser space plane that they're looking to carry their first load of cargo up to the International Space Station, hopefully in 2023. So we could eventually even reach the point of having three different paths forward, and that's kind of exciting to think about.
Yeah, Dream Chaser was one of the uh, proposals for this first set of human spaceflight, and they didn't win that. And they've sort of smartly, I think, converted the spacecraft to a cargo only approach, which is certainly a much easier path to follow.
Yes.
And if it succeeds, then the jump from there to human is maybe smaller. That's the path we saw SpaceX take, and they did so seemingly quite profitably.
And this is the future. I know. I, for one, I want to see that little space plane. I want to see that little space plane.
It looks like a real spaceship.
It really does. Now, while most of what we have tonight is spacecraft, we do get to take a momentary journey into gas giants before returning to more spaceships. So we're going to jump over to learning more about what is the difference between the two pastel blue blobs in our outer solar system. Kim, take it away.
Yeah, we're going to my very favorite places in the entire solar system, which I think is fitting for my last appearance of this season. Going to my favorite places, and that is the ice giant planets, Uranus and Neptune, as you can see on your screen. Um, they are not quite gas giants. They're obviously not rocky planets, and there's a lot that we don't know about them. What we do know is that they're about the same size, they're about the same mass, they have very similar atmospheric compositions, meaning they're mostly hydrogen and helium, and a good smattering of methane and some other sort of hydrocarbon ices. And other than that, we don't really know all that much about them. Um, but given what we do know, it's very strange that they are very different colors in visible light. Uranus is sort of like a lightish blue, greenish, teal sort of thing, and mostly featureless. Neptune is a much deeper blue, has some white clouds, has some dark spots, but given that their atmospheric compositions and other sort of bulk properties are very similar, why are they different colors? Uh, and a new atmospheric model that was just released earlier this week has sort of started providing an answer. And it has to do with one of the major differences between these two planets, and that is their weather systems. Uh, Uranus is very famously sort of like it fell on its side,
Yeah.
it's tilted. There's not much weather, and because that, there's not much weather going on. It gets a lot of solar illumination for a good part of the year, and then it doesn't. And so that means that its temperature and its temperature profile is very constant, it's stable, and its weather system is very sluggish. It doesn't change very often.
A
It
year
it
on Uranus, 84 Earth years. So it's a
yeah.
long
Very
time.
slow, very slow to change.
So
That
it's
means,
essentially going from pole on, only half the planet gets
yeah,
sunlight, to rotated on its side where the entire planet gets sunlight over the course of one rotation.
yeah. So the weather doesn't change all that frequently on Uranus, and that means that its upper atmospheric layers, which are the ones that we see with our eyes, are tend to be very stable. They don't change very much. Whereas on Neptune, the weather changes a lot more rapidly. We've, observed weather systems forming in real time on Neptune over the course of hours or days or weeks. We've seen storms come and go. We've seen these bright, high atmosphere clouds come and go frequently. And what that does is that it creates a lot more turbulence in the atmosphere of Neptune and destabilizes some of the atmospheric layers. And in particular, the atmospheric layer that we care about is a very thick layer of hazes, methane haze. It's one of our favorite hazes in the solar system is the methane haze. And it's very prevalent on both Uranus and Neptune. It glows bluish. But what it does, if you have a very thick layer of haze, think like Los Angeles in the 80s with smog, it all gets a bit hazy going on.
Yes.
It sort of washes out all of the colors. That's exactly what's happening on Uranus, is that because its atmospheric layers, and particularly that haze layer, is so stable, it creates a washed out effect of that blue methane glow. Whereas on Neptune, when things are very turbulent, a lot of that haze actually falls out of the atmosphere deeper into the planet as snow. And so you see more of the blue and less of the washed out haziness. And it's super cool that we have an atmospheric model that explains both of these planets at the same time, which is really hard to do. And the point is really hard to come up with an atmospheric model that can explain both of these consistently at the same time.
Now, can it also at the same time get at what is my favorite little methane atmosphered world, Titan, which is very much mustard yellow? How do you go from cold blue ball to cold stormy blue ball to tiny mustard yellow, not blue ball?
Well, it has two main things. One, Titan does have a lot of methane. It also has a lot of other stuff going on. A lot of other hydrocarbons going on. There's ethane, there's acetylene, there's all sorts of other hazes that get mixed into this atmosphere. The other thing you have to consider is that while all three, Titan, Uranus, and Neptune, are all very cold, there's a vast difference in how cold they are. Titan, being around Saturn, is significantly closer to the sun than Uranus, which is significantly closer to the sun than Neptune. And when you take these methane and hydrocarbon hazes, which, Uranus and Neptune have, tiny trace amounts of those too, when you take those and you freeze them even colder than you have on Titan, and you put them in a way higher pressure situation like you have in the inside of an ice giant planet, you get different properties going on. So there is some chemistry, but a lot of it is just temperature and pressure differences.
That works. That is good enough for my it's all just metals anyways kind of brain.
Yeah. I always love these stories where we're like, here is a basic property about a planet we've known about for hundreds of years, and we're just figuring out this very basic thing about it.
Yeah.
I feel like a lot of the times we get caught in the weeds in places like Mars, where we're like, oh, let me finesse this very fine little detail about Mars, which is a fantastic science place to be. But at the same time, we also have all these other planets that we know so little about, even when it comes to the basics of like, why is it that color?
You always tell when you're talking to an exoplanet astronomer, because they look at a planet and all they want to do is talk about the atmosphere.
It's true. All of them just want to be meteorologists, just not here. Anyways, speaking of planets, Kimberly is not the only planetary scientist bringing us planets tonight. Morgan, what is this juicy news you have for us?
Yes, we're one step closer to the European Space Agency's JUICE mission getting ready to launch. So this is the Jupiter Icy Moons Explorer. It's one of the more tortured acronyms out there, but it's an amazing mission that's going to send an orbiter to Jupiter to study Europa, Callisto, and then finally Ganymede. And when it sort of initially enters the Jovian system, it'll make flybys of Europa and flybys of Callisto before settling into an orbit around Ganymede. And Ganymede is maybe the largest, most interesting thing that we have not yet really understood, really at any level of detail. It's the biggest moon in the solar system.
It's bigger than Mercury.
That's bigger than Mercury. It's also the only moon that has its own actively maintained electromagnetic field. And that's interesting. And it's very, all four of the Jovian Galilean moons clearly had different histories, and we really haven't disentangled why. So to be able to look at all three of the four and kind of understand a lot more is really great. And so the milestone that we've just passed is the completion of what's called integration, which is the fancy engineering term for saying they built the thing. And so the spacecraft has basically, all the pieces have been built, and all those pieces have been bolted to the main structure of the spacecraft. So in theory now, all that's left to do is throw the thing on a rocket and blast it to Jupiter. And that's really sort of closer to being true than not, because we're now less than a year away from the projected launch of JUICE, which is in April of 2023. After launch, however, we will have to endure 8 years of flying out to Jupiter before we get any tasty Jovian science. And so ultimately, JUICE is likely to be a contemporary of the Europa Clipper mission to be launched by NASA, which in theory will be launched in the second half of the 2020s, but take a much quicker path to get to Jupiter by launching on a more powerful rocket, whether that's a Falcon Heavy or an SLS. And so we'll be kind of in this really unique situation of having multiple orbital spacecraft at an outer planet for the first time. And in addition to all of the science they're going to be able to do looking down at the moons, they're also going to be able to work together to provide a much better understanding of the radiation and magnetic environment of Jupiter, which really you can only do with multiple spacecraft. And who knows, if things work out okay, maybe we'll be able to keep Juno around as well. Although, when you're that close to Jupiter, who really knows?
And will JUICE potentially overlap with the Europa Clipper?
I believe that they should. Now, given that neither of them has launched, and Europa Clipper is somewhat farther from launch, it's hard to know for sure. But it'll come down really to what rocket Europa Clipper flies on. If it flies on a big rocket, it may get to Jupiter in only a couple of years. And so it may actually arrive simultaneous almost with JUICE. If they go on sort of a cheaper, slower option, it will arrive later than JUICE. And then it kind of depends on how long JUICE can survive. But I think if I was a betting person, I would say those spacecraft will operate around Jupiter simultaneously. And that unlocks all sorts of possibilities.
That would be so cool to have like a fleet of spacecraft around Jupiter at the same time. Because like one spacecraft is awesome, two spacecraft is better. But if Juno survives too, that'd be 3 who all do very different things in very different parts of the Jupiter system. And that would just unlock so much amazing science. I want that.
I want that too. I want that. We all want many things, and it's never sure in science if we will ever get any of the things we want. And one of the things we didn't know if we were going to get is a certain 4-letter spacecraft.
Mm-hmm. It's true. This 4-letter spacecraft, anyone who has watched me on more than one episode of this show has seen me lament whether we would ever get this special 4-letter spacecraft. But it did launch.
It did.
Last December. It was awesome. And we've been sort of getting little trickles of updates in the 6 months, almost 6 months since it launched. And we've all been like very, very eagerly awaiting when the official first light images would come from JWST, and we officially have a date, and it is July 12th, and that is very exciting.
Yes.
Just full stop exciting right there. And you would say, well, Kim, you've geeked out over images from JWST in the past, and you're right, I have, because we've been getting these amazing alignment, calibration, engineering images from JWST over the past couple months. And those have already just been amazing. You've seen me geek out over them before and just like gush over their amazingness. take that and multiply it by roughly 1,000, and that's what we're going to be getting in July.
So what's it gonna be?
Who knows? It's a surprise. They're being very, very tight-lipped about what exactly JWST has observed as its first target. Extremely tight-lipped. If I were a betting person, I would bet on something that you've seen before in great detail from Hubble.
Yes.
So take that as you will. I would say either a very well-known galaxy or a very recognizable nebula that we will see in astounding new levels of detail in mid and far infrared images, so that you can get those amazing before and after comparisons between Hubble or Spitzer and James Webb. So if I were a betting person, that's where I'd put my money.
Yeah, it's gonna be Pillars of Creation or Orion Nebula or something like that.
Something that not just our amazing astronomy audience would recognize, but most of the public would recognize from a well-publicized Hubble image, is my guess.
I think Pillars of Creation are something else that has had really solid imaging by Spitzer in particular, as well as Hubble and Chandra is definitely a good bet. You know they're dying to do one of those composite images of Hubble, Chandra, the best we ever had before, and now we have. You can kind of hear the movie man voice.
A couple years ago, they released that infrared image of the Horsehead Nebula in infrared, and you saw like the optical from Hubble, and you saw the infrared afterwards, and you were like,
yes,
it's gonna be like that. Is what we're gonna be seeing in July. What I'm also very interested in, I think, is they say that these images, and there'll also be spectroscopic data that come with it, but the images, which is what we're really here for, are going to be so-called full color images, which obviously are not optical full color because this is an infrared telescope, but it'll give us a glimpse of sort of what their color palette is going to be, which is always like, you have to pick a color palette. How are you going to interpret all of these infrared wavelengths into something that our eyes can process? And so I think it'll be just interesting to see what sort of color palettes they're choosing for this. I mean, obviously, probably lots of warm oranges and reds and yellows, but just like what has made Hubble images so popular and ubiquitous is how they've taken how they've produced these images for the wider public, and they're so stunning. And so I'm really curious to see how they will do the same thing with James Webb.
And we are looking to postpone when we record our last astronomy cast of the season to be, instead of on July 11th, we are going to do it after this announcement. Exactly when after this announcement, Fraser and I are going to have to figure out. We were planning to bring you a episode on Did It Happen? And we might as well wait a couple of days to know whether or not it happened. Now, what all do you all have going on that people can go and learn more about and learn more about you? Morgan, what do you have going on?
Oh my gosh, I don't even know. My head has been in the sand at new jobs so much that I just like half the things that we've been talking about today I've never even heard of before. But you can always check out my work over at SciShow, or research spotlights that I've written for ES magazine, alongside and now under Kimberly.
Oh, I don't edit your stuff, I promise. They don't let me. But
and Kimberly, where all can folks find you?
People can always find me at es.org. I did get a tiny bit of a promotion the past month or so, which I'm very excited about, which gives me the opportunity to not just write about space and other Earth science and amazing things that American Geophysical Union is doing, but I also get to edit some of the work of other fantastic writers. Morgan is one of our fantastic writers, but they don't let me edit his stuff. other fantastic writers that we have. And so I get to just see the amazing breadth of talent that we get to showcase, which is just phenomenal. But yeah, all of my stuff is on eos.org. I've been spending a lot of time the past couple weeks writing about the sun, because we're doing a special issue about the sun that'll be publishing at the end of the summer. I think before Weekly Space Hangouts comes back for hiatus, so that's my plug for that. But I'm learning so much about the sun that I feel like I should have known or learned in grad school, but did not. And now I'm refreshing my memory / and learning new things about it. And that's just been a lot of fun over the past couple weeks. And anything I publish, I will advertise on Twitter as well.
That sounds absolutely amazing. And I have to admit that over on Daily Space, our sister podcast and TV show, we have really enjoyed covering the stories that you have put together and Morgan has put together over on eos.org. And if you want to find me when I'm not hosting Astronomy Cast along with Fraser Kane, the normal host of this show, you can find me over on dailyspace.org, which is part of CosmoQuest. And so, in fact, is the Weekly Space Hangout. And this show could not exist if it wasn't for all of the volunteers over at the Weekly Space Hangout who help us find our guests, track down new topics, and recruit the people who, well, like Kimberly and Morgan, can grow up with this show, get their PhDs, and go off into the world, but keep coming back to help this show keep going across, I feel like it's almost a decade now.
Oh, yeah, more than that almost.
Dang. So thank you so much to all of the volunteers. Go check everything out at wshcrew.space. And if you'd like to support this show, you can do so through patreon.com/CosmoQuestX. None of us hosting this show take any of that. It is going strictly to making sure that we actually get content going up into the feeds in all of the various places. So thank you for everything you do to help us out. And go check out Universe Today, where Fraser is. He is really the man behind this machine, and I can't wait until he's back in this chair. So for now, go have a fabulous rest of your podcasting day. Bye-bye, everyone.
Bye.